Welcome students to this online series of sessions on industrial metallurgy. This is session number 2 and we will start discussing about some of the basic terms that are used in industrial metallurgy. In this particular session 2, we are going to discuss the most frequently used term in this field of industrial metallurgy, and this term is phases or micro constituents present in a metal or an alloy system. So these are the topics that we will be covering in this particular session. Okay, so let us see what is meant by this basic term called phase, or which is also referred to as micro constituents of a materials system or a metal or an alloy system. You see, phase of a metal or an alloy system is a region present in the alloy system, in the metal system, which has got its own chemical composition, which has got its own physical state and color, and which has got its own unique set of mechanical properties. Now, if all these things which I've spelled out, the chemical composition, the physical state and color, the mechanical properties, if within a materials system in a particular region, if all these things are same, uniform, you are in a particular phase of that materials system. And if you move on into the material system and you find that there is another region, why it's another region? Because one or more of the things, either chemical composition or physical state and color or mechanical properties, have changed from what they were in an earlier region. You have landed up in another region in the material system, and that's another phase present in a materials system. So phase is a homogeneous region present within a material system which has got its own chemical composition, which has got its own physical identity in terms of state of matter that is existing over there, and also the color that is existing over there, and also the appearance, the structure, the morphology that is appearing over there. And finally, when you are in a particular region which is being referred to as a phase, that region would have its own set of mechanical properties which would be different, separable from other regions which are other phases present in a materials system. So if you talk about this term on the macroscopic level, you see there are three states of matter: liquid, solid, gas. And whenever a material system is in any of these states, it would be a different phase. For example, if you have a particular material system which is in the liquid state, it has got some phase in it. But now if the same material system, because of changes in temperature and pressure, gets into the gaseous state, the phase might be only one, but definitely the phase has changed. First, when it was in the liquid state, the phase is something else. But now when the material system has come into the gaseous state, the phase has changed. So each state of matter represents a different distinguishable phase. For example, here in this figure, I've taken the example of water system. And I'm saying that when water, a pure water system, if you talk about figure A, there is one phase in the system. You may call that phase as liquid water, you may call it as water, you may call it as liquid H2O, whatsoever. And if the same water has frozen, again it has got one phase, but the type of the phase has changed. Again, if it's now now if it's a mix of ice cubes and water, the chemical composition is same throughout, H2O, H2O, but because the state is different, the phases are different. We have one phase, the liquid phase, and we have the other phase. You can call it solid water, or you can call it ice, or you can call it anything, but these two phases, the liquid and the solid, they are now representing different phases. Fine. Then when you talk about a material system, in each of the state, a material system can show different type number of phases. For example, when a material system is in the gaseous state, please remember, if it's a completely gaseous system, the gaseous system will have only one phase in it. And why? Because you take one gas, you take 100 gases, you take them of any type, you take them in any volume ratio, weight ratio, they always form a homogeneous liquid, homogeneous gaseous solution. So you cannot distinguish. It's a complete homogeneous system. So gaseous system, irrespective of the fact how many number of gases and what type of gases are comprising that system, would have only one phase in it. We come to the liquid system. If in a liquid system the constituents are such that they form a solution, then it's always a one phase system. But if the constituents of the liquid system are such that they are forming not a solution but rather a mixture, then you'll have to see how many different distinct regions are getting formed in that liquid system. And finally, students, the most important for us, solid system. In solid systems, if we are talking about alloy systems, you will have one phase present in a material system in an alloy if a particular type of a thing gets formed, which you have done in material science, called solid solution. So if you look into a metal or an alloy system, and if you say, sir, there is only one complete solid solution present in this alloy system, then the phase is one. Yes, in a metal system, you can have numerous examples when there is only one phase existing in the system. But generally in an alloy system, when you look into the alloy system and you say that, sir, only one thing has got formed in the alloy, that is a solid solution, and everywhere that same solid solution is there, then the number of phases present in that alloy system is one. Otherwise, generally, the number of phases would be more than one. Okay. So at the microscopic level, when somebody asks you that, by look into the material system at a microscopic level and tell us how many number of phases are present in it. So there are 4 parameters which you have to evaluate to tell that whether the region existing in a material system is a particular phase and is different from other regions or no. So when you are looking into a metal or an alloy system, if in a region the chemical composition, the physical appearance, which means state, color, and even the physical shape, etc., that you are able to see, the crystal structure and the lattice dimensions of the crystal structure, if all these 4 things are the same, then the particular region where all these 4 things are the same are representing a particular phase. For example, in a particular metal system, you say, sir, everywhere all these 4 things are the same. There is only one phase in that material system. But then if you say, sir, I have looked into the metal system or an alloy system, and sir, in one of the regions, these 4 are the same, but then there is another region where one or more of these have changed from the earlier region. This is a 2 phase. There are 2 phases existing in that metal or an alloy system, right? So when you look into a metal or an alloy system, you have to see how many different regions you are able to see. And how do you find out how many number of different regions are there? In one region, all these 4 things must be the same. And as I said earlier, if all these 4 things are same throughout the metal or an alloy system, there is only one phase in it. But if you find different regions in your metal or an alloy system where there is unique combination of these 4, then it's a multiple phase system. You say, sir, I have 3 different regions present in the material system. In one region, there is some set of values of these 4 things. In another, there is one set, but one or more of these things is different in that second region. One or more things is different in that third region. Your metals or an alloy system is containing 3 phases in it. So I have taken the example of pure iron over here. Students, if you take a pure iron sample at room temperature and atmospheric pressure conditions, if you look into that pure iron, chemical composition is 100% iron, state is solid. right? Crystal structure is BCC, and there is some particular value of the lattice parameters A, B, C, etc. When you are having that sample of pure iron at room temperature, till if you even heat that pure sample till 910 degrees centigrade, none of these four things would change. None of these four things would change. And throughout that pure iron sample, there is only one region containing some specific value of all these four parameters. So pure iron sample at room temperature is containing only one phase in it, and that phase is called alpha phase. And when iron is containing only alpha phase in it, the iron is called alpha iron. When you reach 910, everything remains the same except for this. The crystal structure changes. The crystal structure changes, so there would be a change in the lattice dimensions also. So you have now, rather than BCC crystal structure at 910 and temperatures beyond that, FCC crystal structure comes into picture. So, and what happens because of these two things? Because of any change in these two things, the mechanical properties change. So students, from 910 till 1394, iron has 100% chemical composition, solid state, but crystal structure is now FCC. Lattice dimension values are some unique. So between 910 to 1394, iron throughout has got only again one region, one phase in it. But that single phase is not now the alpha phase. This is a newer phase, a changed phase. That phase is called gamma phase. So I hope now you understand as to what is meant by. So from some books would say 1394, some books would say 1410. Any of these values can be taken, but I think 1394 is more accurate, right? So please take it as 1394. So then from 1394 to 1539, again iron will change its crystal structure, and the crystal structure would become BCC. So the first three things that we had discussed over here, chemical composition, same as was for alpha phase. Physical state, same as was for alpha phase at room temperature. Crystal structure, again same as was for alpha phase. But this is not alpha. The phase of iron that is existing between 1394 to 1539 is not alpha phase, because though these three things are the same, but because of the exceptionally high temperature now, we are beyond 1394, these lattice dimensions are much bigger. So now this phase is not alpha phase, rather it's not even gamma phase, because gamma phase has got FCC crystal structure. This is called delta phase. So this BCC iron that you are seeing is containing a different phase called gamma phase, and as such the iron would be called delta phase, and as such the iron would be called delta iron. And at 1539, iron starts melting. This is the melting point of pure iron, and beyond that, iron does not remain in the solid state, does not have any systematic crystal structure. Atoms are randomly here and there, and the phase of iron is called liquid iron. And beyond 3000, we'll again have iron in the single phase region, gaseous phase, right? Thanks for watching. I hope you have developed some understanding as to what is meant by phases or micro constituents present in the material system. We'll continue with the basic terms that are used in physical or industrial metallurgy. Thanks very much for watching.